Hello and good time of day, everyone. We have a new MLIR open meeting today where Max Levental is going to talk about Nelly. Max, floor is yours.
Cool. Thanks, Mehdi. Okay, so my name is Max. Really quick, I'm a PhD student at University of Chicago in the United States. This is a collab between myself and another student, and the last three names are advisors, senior researchers at the university. And recently I started talking to Nicholas about this. So Nicholas on the IREE Google MLIR side of things. So I'm going to do this in an order where it's like, I'm going to show you some interesting things that'll get you invested in the project and in my talk. And then I'm going to talk about boring things. And then hopefully I don't take too long and we have a discussion afterwards. So all the code is open source, public, there's nothing hidden. You can, this is where it's at. You can, you can't click this link, but you can navigate it hopefully. So this is GitHub. Sorry, I should be more precise. This is my username on GitHub, and this is the project under my, this is the repo. And just very quickly, if anybody's curious or interested, the name, what's the reasoning behind the name? That's my mom's name. And she's actually on this call. So Nelly, it's not a chat GPT autonomous AI thing where Nelly has connected to the video and meeting. It's just my mom. Okay, so the TLDR is I can do these things. I can take this code that's Python, that's executable, runnable Python, just straightforward Python, and emit this MLIR on the right, so left to right, right? So I can do conditionals, I can do loops, I can pass in various kinds of MLIR standard types, so memrefs, tensors, stuff like this. I can also support things like modules and dialects that require modules. So that includes GPU and transform, and I can run them too. So, right, the previous slide shows a very, very simple transform applied to a loop and unrolling. I stole some passes from Upstream and plugged them in, the transform dialect interpreter, run it, and it unrolls the loop in some step size. And so this is just another slide showing that it's runnable. And so these are all screen caps or snippets from tests that are in the repo. And so one of the tests that runs on every commit is do this matmul and compare against the results produced by what NumPy would give you. Yeah, okay. So that was the teaser, and hopefully those were interesting enough, and maybe I didn't go through them, like I didn't pause long enough for you to soak it in, but hopefully you're invested enough to listen through the boring stuff of like how that works and how I got it to work and implemented it. So the outline for the talk is, why did I do this? Why am I working on this? What are the goals of this thing? What are the non-goals? Like particular things I want to avoid that this thing looks like and implicates or might imply that I'm not trying to do. How I managed to do some of the things that appeared on the previous slides. And then the discussion part will be like, what can I upstream? And then some other small questions that I hope to get feedback on. So I'm going to say at the outset that I will probably get more out of this meeting than you will get out, because I'm not doing anything very fancy, but I hope during the discussion to learn some things from the community and the more senior people on the call. So the discussion has some questions. I have some questions that I'm going to pose. Okay, so the first thing that I want to say before I discuss anything is 95% of what's possible in this project is a direct result of upstream work on the Python bindings themselves. Not to say anything of MLIR itself, but like just the work that was done on the bindings and the layering and the table gen that admits the builders and stuff like this, right? Like the 5% that I've added is syntactic sugar, some dirty hacks essentially. So I want to thank these people, and there, of course, many, many more people. I just kind of like scrolled through the commit history, the git blame on that directory in MLIR. Okay, so what's the context? What's the story? Why did I start working on this thing that is an MLIR emitter? Why am I not working on like code gen or something like that, which is what most people I think would direct their efforts at if they were going to work on a compiler project. So about a year ago, I started on a project, and it's funny, Mike's on the call. I started on a project that was like an FPGA-esque, like start with a neural network, some transformations on it, lower it to FPGA, and possibly pass through MLIR and something else to get there. And so I started playing with circuit. So I started in the adjacent neighborhood of circuit, and I didn't know anything. I literally had never seen LLVMIR at the time at which I started coding that other project, right? I knew that MLIR was like important, and I had seen some tutorials, or I had seen some videos, and I went through the tutorial, but basically no compiler experience, no nothing. So I didn't know what any of these things on the left-hand side, far left-hand side were. I didn't know that what loop fusion, loop normalization, loop tiling, and unroll and jam were. I knew that they were important. I knew that they might end up I figured they might end up being important for this HLS, high-level synthesis for FPGA project, but I didn't know how they worked. And I go to MLIR and I'm like, how do I turn the knobs? How do I crank the wheel? How do I put in some IR and run a pass in order to discover what these passes actually do, right? So these are, either affine loop fusion or SCF loop fusion. These are passes that we have available in MLIR, and you want to run them on something to figure out how they work. Now, the more principled approach to figuring out what loop fusion is to read the papers or something like that. But I'm kind of like this bash my head against the wall developer rather than read the paper developer. So I want to run code and kind of like train my own neural net in my head, input, output, what's the structure underneath, right? And there was no way to do this with just for loops. I mean, that's not to say that you can't write the IR. You can by hand write for loops. You've always been able to do that, right? What I'm saying is there was no simple way to write in a programming language that was familiar to me. I mean, maybe Polygeist was around at the time, but I don't recall. I probably didn't understand what Polygeist was at the time. And so even if it were around, I didn't understand how I could write the C++ and get affine for loops out. The Python bindings existed, but they're kind of strange, and I'll get to that in a second. So what's available? This is available, and so this is a diagram from Lei, who works on IREE, and I think a large part of this was inspired by some presentation that Alex gave, I think. And this basically lays out the difficulty for me as a noob, which is the programming, like MLIR is a compiler framework stack tool set. You're not meant like program MLIR. You're not meant to write MLIR as a programming language. You're meant to pass it programs, and then MLIR will transform those programs. So it doesn't really like that desire to be able to emit for loops and then transform those for loops is kind of weird. It's not how MLIR is supposed to be used. You're supposed to program at a very, very high level of abstraction, and then MLIR takes care of the rest for you, right? And so like professional users or knowledgeable users of MLIR have no problem, have no friction around the thing that I had friction around, which is I have no idea what I'm doing. And again, I'm a really weird case. I'm a compiler, researcher, student in a distributed systems group. In any other instance, I would be in a compiler group and they would be able to tell me these things or explain these things to me, and I wouldn't have to learn it from the source code. But whatever, it is what it is. And I wanted to figure out how MLIR works. And I had no real straightforward way to generate MLIR, save for these very high level frameworks. And what happens when you try to emit MLIR starting from something high level like Torch, like PyTorch, is you get a whole bunch of stuff that's, again, like initially was very confusing and clear to me and unknown to me. So for example, I know what a convolution is. It's 7 nested loops. When I lower a torch.conv.nn into conv2d, I get these 2 other loops. Initially I had no idea what the reasoning was. And in a bigger program, of course, right? Like if I don't even pull out the conv2d from some neural network, if I just try to follow the examples and I push an entire ResNet through, God, it's just overwhelming the amount of essentially noise that you get if you don't know what you're looking for, but you know what a convolution is. So now I write these 2, one of these loops is for the initialization of the bias, and one of these is to preserve value semantics. And a year later, that's very, very clear to me. But a year ago, it was just German or Chinese to me. And so what do you do? So I looked around, I went, in order to learn how MLIR works and learn what these transformations were, I did discover the Python bindings. They exist. They look like the stuff on the left. You have to instantiate an insertion point. You have to manage all of the attributes that you're going to use to pass the builder and all this kind of stuff. It's very, very different from what you see in traditional, in like MLIR itself, right? The MLIR itself is not about emitting MLIR, it's about transforming MLIR. And so you see primarily like rewrite patterns, right? So you can't even triangulate between the two if you want to figure out, well, how do I generate the MLIR that is passed in this pattern rewriter? The pattern rewriter doesn't actually tell you anything about what the input. Again, this is nobody's fault except my own for deciding to do compiler research in the context, like I'm a child without supervision, right? Like my research group doesn't know anything about compilers. And there are people in the department that of course do, but like my nearest and dearest friends couldn't answer any of my questions for me. And just by the way, I forgot to say this, a lot of the people on the first slide have helped me. I've had conversations with people, and Mike, for example, had a lot of conversations with me initially about FPGA stuff and compiler stuff, and that was very, very useful. So the community is fantastic. It's just the code is commercial grade, weapons grade code, and it's hard to like, without any supervision, it's hard to parse, it's hard to triangulate between these disparate things. Okay, so that was the trouble that I had. And I quote unquote, soldiered on, and I worked on the HLS project, and all the while my skills improved and I got to understand what MLIR does. But still, I wanted to improve some aspects of that onboarding, essentially, for whoever might come before me and for myself as I continue to work on this thing. Like, I don't want to, even though I can now write probably MLIR without tripping the verifiers, I don't want to. I don't want to write it by hand. I think, so the LSP exists, so Rivers project exists. I'm actually not sure if you get like tab completion or IntelliSense or whatever in VS Code if you hook up the MLIR LSP. So maybe that's really good, and maybe it's completely mooted if I just pick up the LSP and just write MLIR. But there might be other reasons that you don't want to just resign yourself to like, hey, I'm going to write IR as if it's a programming language without any of the tools that are available, or without many of the tools that are available for traditional programming language, like refactoring. And again, maybe the LSP does this, but runtime kinds of things where like I want to inspect what the values are, right? Because again, IR is IR, you parse it, you transform it. You can't put a breakpoint as you're executing to figure out things about such and such operation, right? Again, it's all there in the IR. That's the point, and I realize that. But it's not easy to use when you don't know anything. Okay, anyway. So the goals of this project are, the first one, the foremost goal is it should be easy to use for noobs, complete noobs, which is why it's in Python, because I'm a complete noob, essentially, right? Like, it's like the traditional thing where like Python was the first language that I learned very, very well, and I've stuck with it because it's very easy to use and it's very easy to inspect. I could put breakpoints wherever I want. So it has a very like gentle complexity slope or something like that. If the thing is architected right, the user won't be overwhelmed. There's no like, oh, the compiler breaks and you get no feedback whatsoever, or you get very like veiled feedback about what you did wrong. Anyway, whatever, like template compiler errors in C++ are well known to be confusing. Whereas in Python, you can put a breakpoint and you can poke all the variables and you can know what's going on. Okay, so the first thing is easy to use. Hey, you can put a breakpoint, you can figure out what the operation was that was just currently emitted. You can hit dot operands and see what it operated on and what the result types were and all this kind of stuff. And that's all provided, again, by upstream bindings. I did not layer this or design this in such a way. I'm just availing myself of these things. The second thing is that whatever I implement should be simple to understand. And I have this like pseudo nuanced distinction between easy and simple. Easy is just works, I don't have to think about it. Simple is, given some effort, but not an inordinate amount of effort, you can understand it. So that means like, and I'm missing a parentheses, no kind of weird things that I have to read a category theory book or Turing's thesis in order to understand. And no kinds of things that are just like way out there. I'm being very farcical and very sarcastic here. I don't think that anybody's like, I mean, there is a quantum assembly language MLIR project, but again, this is kind of a joke, right? That I'm bringing up quantum computing. So simple to understand. So I keep whatever implementation that I like, whatever code that I've written to make all this magic work, I keep it as compact and simple and like nothing super fancy, except for the 3 or 4 things that I'm going to mention, right? Everything I'm like small wrappers essentially around the upstream bindings. Okay, the third thing is it should be easy to get. One really hard thing, and I think this is like I'm not like some grandstanding member of the community, but it's a serious barrier for people that don't have fast internet connections and 32 cores to start playing with MLIR, because it's a 6-hour recompile, or it's a 3-hour recompile, or it's a 1-hour recompile, right? If you change some very, very shallow or deep, however you want to think about it, header, for example, right? And I'm lucky. I'm very lucky. My advisor supports me, and yeah, I mean, so some of us who have like powerful machines and stuff like this, it's good. Like on my M1, it's 10 minutes or something like that, and on my workstation that is, again, like provided by somebody else, that's fine. But when I first started a year and a half ago, I had a 2011 MacBook, right? So I had an i7, exactly, right? So and some people, I have a new student in the lab that I'm kind of like mentoring, who I'm onboarding onto the project, onto MLIR. And before he got his newfangled machinery, he had also an i7 from like, I don't know, 2014. He has some Windows machine that he spent a lot of money on when he first started undergrad, and it lasted him all through undergrad. And now he's arrived, and he hasn't gotten his new kit yet. And it takes, I told him, hey man, you should need to day one ask our advisors for new equipment, because you're going to kill yourself trying to recompile. Okay. So that means that I have, what have I done to this? What does it do with anything in the language? It doesn't, but I've set up release builds of LLVM to include MLIR. And those are those are essentially, like downloaded when you try to pip install. And so you don't have to compile MLIR from scratch to use this. You can essentially pip install it, although it's not on PI. Okay. And then the last one is, I don't want to change the names of anything. I don't want to oh, even though if I disagree with some naming scheme, I don't want to make it my own language. I want to reflect as closely as possible I can the semantics of MLIR, at least as far as the dialects and the operations go. Of course, again, MLIR, like MLIR opt and all these things are not about emitting MLIR. So there's no way to mirror the semantics of how MLIR is emitted. Everybody chooses their front end, and the semantics of whatever the emission is for you to decide. I'm saying as far as the dialects go. Okay, a lot of words. Non-goals. I am not trying to compile Python. Even if I didn't understand what I was doing when I first started in December on this thing, and I started on Nelly in December, I think I said it at some point. Like I gave a student presentation, like, I want to compile. I said the standard thing that I had read, I was parroting. I was like, I'm going to compile numerical Python. And I'm not doing that, because that is an enormous project, and there are plenty of other people doing that, and they are all better at this than I am, right? So for example, Marcus, who I talk to pretty frequently, is like a C++ wunderkind and answers all my C++ questions in like 2 seconds, has this thing. So PyLR, or however you pronounce it, is exactly this, Python to MLIR compiler. And then another project that's staffed, right? Like this is an Intel staffed project. Numba MLIR does the Numba trick on Python, but emits MLIR, right? And so this guy is, again, probably better at this than I am. He's been doing this for much longer, and he's also fully staffed on it, right? So I have research goals that are not PLT language design research goals. I'm only doing this thing and working on this thing to make somebody's life easier, one person at least being mine, right? The main actual focus of my research is kind of like polyhedral stuff. It's not the language design aspect of this. Okay, anyway, non-goals. Okay, so how do you do this? How would you build a front end? There are the standard things of like, the first one is like, I'm going to build a compiler. I'm going to analyze the source AST. I'm going to do type inference. I'm going to do control flow analysis, build a compiler. And like I already said on the previous slide, that's an enormous project that's very hard, in particular for Python, because of the dynamism of the types and all this kind of stuff. And I don't want to do that. It's just enormous amount of work. And again, I don't want to build a compiler. I want to do polyhedral loop transformation research. My thesis is not going to be on some new front end. It's going to be on some new polyhedral transformation. And in addition, it completely throws away all the work in the bindings, because you're doing source analysis. You're not running the program. Again, obvious, but I tried this, right? So I have attempt 1, attempt 2, attempt 3, attempt 4. My first pass at this was, because Python makes it easy to parse the AST. It's all in the standard lib. I'm like, I'll just do it. And I did it, and it took me a week, and it was rickety, and it wouldn't have gone anywhere. So I gave up on it and immediately realized what I really wanted was an interpreter. I wanted to interpret the Python. I wanted to run the Python. So what's the next attempt? The next attempt, and there are several versions of this, implement the CPython interpreter, but in Python, right? I don't care about compile time, and I don't care about runtime, because I'm not running these programs on data. I'm running these programs to emit IRs. So I'm not really worried about like, hey, the interpreter's slow. I don't have that problem. I don't have the same problem as the CPython developers have. So implementing the Python interpreter in Python enables me to like hijack the bytecode instructions and do what I want. So for example, one of the things that you want to do is, instead of the really simple thing is like the iter args should be the return value of the range operator, or the range primitive built in Python, right? And you can't overload range. You can substitute the function call. You can do that, right? But it's, if you want to, in the stack frame of Python, play a hot swap thing where Python runs and parses a for loop, and then instead of returning I is 0 to 10 integers, I is 1 iter arg handle, you can do that if you hotwire the Python interpreter, right? Hotwire or re-implement whatever bytecode instruction handles iter args, right? And because it's written, if it is written in Python, you can make use of the bindings, right? So I can substitute things like, if I see constants passing through my re-implemented Python interpreter, I can immediately wrap them in arith.constant, stuff like this, right? And I tried this. I kind of like copied and pasted from ByteRun, which is a GitHub project, which is really well done also, but it's brittle. And also you end up having, and I haven't figured out, I still want to think about this, right? Like, it would still, I think, be useful to have an implementation of Python where 90% of the bytecode instructions are handled by the stock interpreter. I just override the ones that I want, right? I don't need to handle exceptions. I don't need to do any of that kind of stuff, stack unwinding, whatever. I just want to overload a couple of them. I want to overload like load name, stuff like this, right? And I haven't figured out how to do this, but anyway. Okay, so is there a better way? The thing on the left is kind of speaks to what I was just saying, which is maybe you could hijack tracing and debugging, because in the set trace, sysset trace, you can debug based on opcode. So you can say, I only want to debug the load name opcode. But the thing, and you can do this, and you can, so you'll drop into essentially a callback every time there's a load name bytecode instruction run through the interpreter. The thing is that you can't manipulate the stack, or at least you won't be able to very soon. So in 3.10, you can push and pop to the Python stack, but then they eliminate that API in 3.11. So that was like not going to work out. It was going to work for 3.10, and then eventually it would be worthless, or I'd be stuck on 3.10 forever. Then the second idea is, and this is a brilliant idea that didn't occur to me, and I would have never thought of this had I not chanced upon this package, which is instrument the AST nodes. So Piccolo, this thing from some guy at Facebook, what it does is it walks the source AST and wraps some of the operations, like for example, AST.call in a conditional or something like this. It essentially wraps, it like finds the call AST nodes and inserts into the AST a hook. So it hooks the AST, it hooks based on the AST nodes, and it rewrites the AST, and it works beautifully. It's amazing. Like, it's essentially, if I understand these terms correctly, Lisp macro expansion for Python, and it's wonderful. It works. Like, I've used it for other things, so it'll rewrite, for example, all of PyTorch. Like I was doing, he has an example where he does lazy imports. So all of the imports in every package that you load and every module that you load are wrapped, right? And he makes it lazy because he returns like a lazy symbol and stuff like this. And so I ran it on PyTorch in order to only import the things that I want, for example, and it didn't break. Like, it worked. And it's just amazing, because if you're rewriting the AST of like whatever hundreds of files in PyTorch that are Python source files, you're like, it's got to miss some corner case, but no, it works beautifully. But the problem with this is it's rewriting the source. And that's like black magic that I wanted to stay away from, because it makes the implementation hard to debug for the new user, the implementation of Nelly. Okay, so what's the solution? Finally, I'm at the thing where I talk about how I did what I did. And essentially, I take little bits and pieces from each of these three approaches. So now I'm going to go over in stepwise order, like in order of increasing fishiness, what I did. So the first thing is I want to overload, I want to do operator overloading on Python values that correspond to the stuff that the Python bindings return. So for example, .constant.result. I want to be able to do arithmetic on the value, the like MLIR : value, or the Python pi value thing, right? Why? Because it's obvious, right? Like an arith.constant should multiply with another arith.constant if the types are correct and all this kind of stuff. And it's easy. It's a low-hanging fruit. If I'm able to do that well enough, then I'm able to simulate arithmetic. People will be able to write arithmetic operations in Python, and it'll emit the corresponding MLIR arithmetic operations. So this is, on the Python side, very low-hanging fruit. You just, like, it's shown in the bottom right-hand corner. You apply some wrapper, you wrap the result of some operation, and you overload the operations on that wrapper. This is like a very standard thing, right? The problem is that upstream, and I think, you know, like, again, I don't have a lot of input from like compiler researchers, so I talk to myself a lot, and my kind of like feeling for why this is done, why you're prevented from being able to do this, is because professional software engineers err on the side of encapsulation, encapsulated hidden surface APIs rather than public APIs. So what I'm talking about is that all of the classes in IR module.h, none of them are exported. They could be exported so that they can then be reused, subclassed, et cetera, in Python extensions of the upstream bindings. They're not. So those symbols aren't visible. You know, Mehdi understands a little bit because there are a couple of posts for me. I've been fiddling with this kind of thing for like 6 months now, where I'd like to like get symbols. I'd like to like load blah, 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 shared libraries and have access to the code in the shared libraries that are from the default builds of MLIR, right? And one barrier to doing this kind of thing, which is, hey, I want to subclass the Python bindings in C++. For whatever reason, is the symbols aren't exported. They're lowercase t instead of capital case T. The default visibility, sorry, the visibility is hidden. It's not default. So the first thing you got to do is patch that. If you want to subclass the C++ classes and do stuff in C++. And I do that, and I do it using kind of like a really dirty regex in the CMake. It's you know, it works, it's fine. It only matches on the stuff in that header and blah, blah. So it works every single time, and it's been consistently like robust for months now, but it's, you know, it's not the right way to do it. Really, what should be done is like, there should be a discussion about why those classes aren't visible, and are we comfortable with them being visible? Is there a compile path within which we would allow them to be visible, stuff like this. The second thing is all of the modules as defined with respect to PyBind. So there's this Py module local. So you can specify that a module is package local, or sorry, not a module. A class is module local, right? And that means that they won't be imported. That means that essentially it doesn't get put into the double under all thing. It's not exported from the Python module. And so you therefore can't subclass those values. Forget C++, you import you know, MLIR.IR from MLIR.IR import value. That thing can't be subclassed because it then gives you some error about you didn't call the constructor. You didn't call the double under init or something like this. So you got to drop those two in order to be able to subclass things in Python. So again, I do this with the regex. It's kind of like a hack. There should be another discussion around this, blah, blah. Anyway, whatever. Once you do these slightly questionable things of removing these things, you can subclass anything that you want in both Python and C++, and you can wrap the operations in your symbolic, whatever proxy, blah, 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 abstract value, and you can overload the operations, and you get arithmetic, and you get all some nice things like tensor slicing, right? So the kind of thing that again, very natural, is like we have tensor.slice or extract slice, and we have memref load and store, and those map, you know, basically one-to-one, you know, modulo the affine stuff, basically one-to-one with indexing in Python. So you overload get item, and you can grab stuff. So that get item corresponds to memref dot or affine load, and the next one, the index store, you know, the index write corresponds to a store. So again, nothing very fishy, nothing super fishy. Okay, so the next one is where the fishiness starts. Okay. Python, for whatever reason, doesn't have lexically scoped regions or blocks or whatever you call it. What I mean is values will leak out of for loops and they will leak out of conditionals. And everybody knows this. It's like one of the first things you get bitten by as like a noob Python programmer, right? So you can't do escape analysis and you can't do stuff. You also you also can't like register some kind of deferred close like you can do in Go, right? So what I'm saying is I want to emit affine for loops here. How do I do that? Essentially, the only thing that I can do is sorry, did it switch? I feel like I'm missing something. Missing a slide. No, sorry, here, I went too far ahead. Yeah, I went too far ahead. So the only thing you can do to indicate like, hey, to the emitter, to this thing that is the front end, I'm done with the for loop. Please close the brace, is you have to put a function call. So the affine range turns on the affine range for loop, right? It's not overloaded range, although you could do like the type def range equals affine range. The affine range turns on the for loop within the scope, right? Context manager, all this kind of stuff. Enter the scope of the context manager, exit the scope of the context manager, put in the yield or whatever. And I'm not handling loop carried dependencies. So this doesn't allow, and I don't know, I haven't thought about it, but this does not allow for loop carried dependencies. You can't do iter args for any of this kind of stuff, again, because of the escape analysis kind of stuff. But anyway, you have to do a function call at the end of each for loop body to close the for loop. Okay, but that's annoying. That's weird. It completely changes the Pythonic. Like, sure, you can do it, but it's like Pascal or something where you have to have an end now. This works. And this is kind of like a joke, like, where'd they go? Well, how did you hide them? Where did you put them? How did you do that? Answer is very simple. And this is, again, where the fishiness starts. I do a little bit of source analysis. So you can, so there's a decorator. The decorator will rewrite this function effectively, right? It'll look through the source. Right? If you do an AST traversal, you can find the end of the for loop. And you can insert on behalf of your user those same affine, again, it hasn't switched, those affine end-fors, or for conditionals, end if, all this kind of stuff, right? So if you do a minimal amount of AST traversal and analysis, you can get a whole lot of bang for your buck. Okay, next one, most fishiest, the fishiest one, most fishiest. So again, if you do the source traversal AST analysis thing, you can handle stuff like this. You can rewrite the thing on the right. So essentially the flow should be the other direction. The error should go the other direction. If you do AST analysis and it says rewrite AST equals true, you can insert the calls into the right-hand side that make it look like the left-hand side. And then you can imagine how the calls on the left-hand side correspond to turning on an if, the context of a conditional SCF, and then turning it off, closing the context, right? So that's very clear. For a single branch, if this is fine, you don't need to do anything else, right? But of course, what's the point of a conditional? I mean, you actually, I think, I don't know, I'm not gonna say, but you can have multiple ifs. Cool. You can have a sequence of single arm ifs. I don't know. I guess that's useful in some instances, but it's not, you want an else, right? So how do you do this? Right. And this is important, right? Like there's a fundamental kind of thing here, assumption, a branch is a branch. There's no, like, what are you going to do? The next thing is a joke. Do I have to implement a non-deterministic Turing machine where I take all the branches all the time and I don't know, never completes or something like that, right? So the point here is, if you run this program, whatever the semantics of these operations, the baseline implementation of CPython will only ever take one branch, right? There's no debate here. Okay. And yet this works, right? So this is, you can run this thing on the left and get out the MLIR on the right. And it's like, how did I do this thing where I caught, essentially like inspected, caught, snooped on the other branch when the if was taken, or when the true condition was taken, or the false condition was taken? And I'm not doing source analysis for this trick. I'm not going to do a source analysis because I don't want to do a source analysis because I want to avoid source analysis as much as possible, but also because you get into this of like, I have to do the NFT thing, the NP thing, non-determinism thing. I got to really execute all the branches. Well, I got to crawl all the branches. Sorry, I got to do like a depth first, a breadth first traversal of all the branches. Okay, so the answer is, again, this is a very dirty hack. I write the AST, which so it might feel like I'm like saying I'm not going to do something and then doing something worse. I'm going to rewrite the bytecode. I'm going to take out the jumps. I'm not going to, I do it, right? So, right, Python is compiled into bytecode, and then the bytecode is interpreted by the VM, stack VM in CPython. So an if translates to a jump, right? A condition, this is again, like kind of like basics. Hey, a branch is a jump. You test the condition. If the condition is true, you don't branch, and if the condition is false, you do branch, or whatever it is. But sorry, you do jump or you don't jump. But either way, the bytecode instructions, some subset of them are never executed. The subset that's not executed, that's the one of the branch that wasn't, those correspond to the branch that wasn't taken. So just take them out. Just, I mean, in fact, you have to no-op them because there's some stack size calculations that you run afoul of if you just remove them. So you know, the bytecode instruction set has a no-op operation, so I no-op them. And so what effectively happens is you fall through all the instructions. It's like you removed, I mean, whatever, you guys get it, right? You take all the branches out, you execute all the instructions. If this was data, that would be completely insane, but it's not data. I'm not trying to manipulate data. I'm just trying to emit the operations. So again, the way that this works is I insert these kinds of function calls that turn on and off. So the order is I insert the function calls that turn on and off the scopes, the regions, and then I fall through the entire conditional. And that gets me, you know, it's not a trace. I don't know. It's a non-deterministic trace, whatever you want to call it, of the entire program. Okay. So that's the end of implementation details, and the summary is that the nutritional, like how nutritious is Nelly. It's, as I try to keep the fat to a minimum. What I'm calling fat is metaprogramming, so that's AST rewriting and bytecode rewriting. Those two cases that I just discussed in unnecessary detail, possibly, are the only instances. Everything else is wrappers and like massaging of APIs and stuff like this. There's a whole bunch of sugar, syntactic sugar, to like make the bindings nicer to look at and blah, 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 stuff like this. And it's all built on a, you know, strong foundation of like the upstream work, the layering that was done when those were designed, when the Python bindings were originally designed. And so what I'm really doing here, what is this thing that I'm doing? I'm not even building a front end. It's kind of like a language design exercise on my part, because I'm not doing a majority of the work. I'm punting a majority of the work to the bindings, the actual IR emission. I'm not doing AST analysis. I'm not doing control flow analysis. I'm punting and doing weird stuff. And I'm basically like figuring out what's an interesting, useful, convenient API for building an MLIR IR emitter. And so it's like this thing. It's like when you go to the art museum and you see people sitting in front of great works of art and they're sketching it, right? They're like, one day I hope to grow into somebody that's as good as that. So, right. So that's me. And I'm doing a sketch of what professionals and more senior researchers do when they design language front ends or compiler front ends or whatever. Okay. So that's the end of me, or that's the end of current work, I should say. That's the end of current work. And so there's some discussion that can happen around what can be upstreamed. As far as the Python goes, I think, I don't know, you know, like it would take somebody who cares enough to look at the examples and then look at the implementation to decide that this is good enough to upstream. I don't know. I don't know if this is valuable. I think I've heard many times, like I've talked to Stella about some of this stuff. And at some point she said, and again, I don't think she was being dismissive or anything like this. She was saying like the goal was not to design a language front end. It was just to build bindings to make things like a little bit easier to use, but they're not aiming to build, you guys, you know, whoever owns that code, like primarily isn't aiming to build a front end. So I don't know how much, you know, new features they would be willing to take on. I don't know. The thing that could be useful, at least as far as, you know, like I have validation for being useful, is what I am doing as well is pulling stuff in from various places on the CPP side. So I pull in stuff from tests, like I mentioned at the beginning, I pull in the test that runs the transform interpreter so that I can run it as a pass in the set of passes. So I basically I lump it in, and then I initialize that pass as part of the initialization of the library, and now it's available as a pass to be run by the pass manager and all this kind of stuff. So that's a test that already exists upstream. But in addition, in trying to write this up and kind of pitch this to a journal or a conference, is I want to get fast CPU and in weird places, and in GPU in weird places like edge devices. And so I'm fiddling with, I'm trying to incorporate IREE stuff. I'm trying to incorporate optimization pipelines that exist in IREE. And this is where the this interaction with Nicholas comes about. There's a post on Discourse where he's like, I'm putting together this kind of tutorial-esque demonstration of some of the flows in IREE. And Mehdi responds that this is confusing because it's purely in IREE. Are you guys in IREE? Are the IREE folks planning to upstream? And Nicholas is like, yes, but we need help. And I'm like, you have my sword, you have my shield. I would like to help. IREE's cool. The GPU optimization, the transformation optimization work is very, very good. They're getting really good performance, but it would be great if it wasn't in the context of just another thing. Like IREE is a downstream MLIR project. It's hard to say that it's so divergent from MLIR that it presents a real challenge to anybody who's familiar with MLIR, but it's not upstream. You want, and a lot of people want this, right? I'm not the only one that wants this, that desires this. Nicholas himself says he would like for these things to be upstream, whatever transformations that aren't IREE dialect specific to be upstream. In fact, they take the maintenance burden off themselves to some extent if they upstream. So I'm pulling in CPP into Nelly from IREE, and so therefore it functions as a staging ground for things that can be upstream to MLIR, because I don't have IREE as a dependency. I did not pull in their dialect stuff. I have pulled in some of their transform extensions, but again, it works independently of, I don't know, whatever. It's just I don't have IREE as a dependency. This stuff works. That means it could go upstream if people wanted to go upstream. Okay, so that's about Nicholas and work. And I was planning on showing some performance slides or maybe a demo, but I got caught up working on paid work, Torch MLIR stuff yesterday, so I didn't finish it. And now we get to the discussion part. So here are the three questions that I posed to the audience, the community. And the first one is purely self-serving. I'll be completely honest. I need to write this up as a paper to validate, justify my stipend. And I have some idea of why it's useful and interesting and cute, but I don't have a really good pitch to a journal committee or a conference committee. So if you think this is useful, can you tell me why you think this is useful? And I'll probably paraphrase when I write the abstract or something like this, right? So I'm serious. I think this is a nice thing for beginners for sure. I don't know if it's useful for compiler engineers that are professional compiler engineers, because you start at a high level. You don't really care about what the for loops look like or the lower level dialects. You're not, now understand loop transformations. My next step is to understand vectorization. So now I can do that. Now I can emit loops and go to the vector and lower to vectorization without any of the kind of cruft that you would get if you start at a convolution and then try to lower all the way down to vectorized code or vectorized IR. So I'm in a good position now to learn about vectorization. A professional compiler engineer already knows about vectorization, is very familiar with the dialects, or at least the idioms of the dialects. And so that's not very useful for them. One place that it might be useful that occurs to me is maybe I want to write micro-kernel, quote unquote, micro-kernel implementations of some operations that are currently not supported. I don't know what those are, because linalg generic is generic. But if I want to write some for loop implementation of some kernel, there's really no straightforward way. I think I'm right on this. Save for those two projects that I mentioned, which is PyLR and Numba, MLIR, there's really no way to write those for loops in a convenient way. You can write the IR, but then you're just writing IR. So for example, in IREE, you see parameterized. I've seen Nicholas's stuff and it's parameterized. You want to parameterize the IR. The way that you parameterize it is by sed. You edit the file, right? You edit the text file that defines the IR. Instead of emitting IR, you've written the IR once, and it's parameterized by matmul dimensions, right? So it's M, N, and K, and those are parameters, and you can sed them out. So that works, and people do it, and you said the file and feel sad about it. Yeah, that's clever. Yeah, okay. So this might be useful, helpful if it were super solid. Like, I don't stand on any of this, so don't use this for anything except to, like, I don't even know, right? Like, the tests work. I have a pretty large test suite in that repo, but I don't know if you verge off the beaten path, you'll probably fall off the side of the road into a canyon very, very quickly. But if it were polished up, it could be better, right? And therefore, it might be useful for generating microkernels. But then again, what subset of the community really cares about generating microkernels? I have no idea. Reduces test dependency, like not dependent upon desire. That's yeah, sure, right? Like, some people don't like the Python interpreter or don't want the Python interpreter in their production stack. Sure. 100%. Like, I get the point. I mean, the point, the way that MLIR is correct. There's nothing that I'm claiming that I've discovered that is a novel flaw, because MLIR is built upon decades and hundreds of people years or thousands of people years of compiler experience. So there's nothing like, oh, I'm a noob and I came and there's a flaw. No, it's just, and again, the point of the first question is like, I need to write this up and move on to the polyhedral stuff. And so I need a pitch. And so if you think of something cool, and if you don't, then I don't know, I'll send it to like some open source journal, and it's like, hey, this is the PLT front end and it was a language design experiment. Okay. The second thing is, speaks to like the difficulty of getting a binary released version of MLIR, right? So the releases happen. And I think actually, Mehdi, you said this to me at some point, probably like 6 months ago, like, you're like, as far as MLIR goes, the LLVM releases are irrelevant. I don't know. I didn't press and I didn't ask. You know, again, this isn't a confrontation. I'm just recalling what was, and I'm like just repeating. This is not an accusation. There are no MLIR binaries in the repo, in the releases of the repo. Fedora has releases. So Fedora releases MLIR as a binary, or RPMs, right? And then for those of us that aren't on some Red Hat CentOS thing, you can finagle with the RPMs. Okay, so that works, I think. So like I said, I have LLVM releases that track the commit that Torch MLIR is pinned to, because like I get paid to work on Torch MLIR, so it's useful for me to be have parity with them. Again, I don't know what I'm saying here, because I don't really want to propose. I don't want to really volunteer to like run a build bot, because I think that's a lot of work. And hopefully soon I will be a full-time paid employee of some company that is involved in MLIR, and then I'll be able to take on that professional responsibility if it's still unfilled. Versioning. Versioning. Oh, okay. LLVM version. Yeah, sure. I mean, I don't know what the LLVM versioning scheme means at all, because everything moves so fast anyway that like as soon as the 16.0 release is released, the next day there's some grant. I mean, I don't know. I mean, I'm bullshitting a little bit. I actually don't know what the versioning scheme really implies, because as I can tell, everything moves very, very quickly. So I don't know what I'm suggesting here. Like a builder bot, I don't know what work is involved. I can get things to build. So I have in my LLVM minus releases subrepo, I have builds for Linux and M1s. So I have cross-compiled builds, right? Like I use Docker cross and I build a cross-compiled version, so that for me, it's easy to work on my laptop, which is an M1, and on my desktop, which is a Linux machine. And I also have an Arch 64, like, so not M1 ARM64, but Arch 64, because I've been playing with Raspberry Pis and just not Apple ARM silicon, but other people ARM silicon. So I have three different releases. And I also have the wheels packaged up. So one thing that happens that you build, if you build MLIR from source, is you do get the Python packages and the libs are there, but the loader paths are all relative to where they are in the build tree. And you can do, so there's no wheel, but you can make a wheel, right? Like, again, I'm just adding a little bit of sugar on top. You can package up those bindings as a wheel and you can rewrite the loader paths and everything works fine. So Nelly has pip wheels based on that, the experimentation. And in that LLVM releases repo, I also released the wheels for the upstream pure bindings. Okay, the last thing, and I'm at 55 minutes, so it's perfect timing, is I like Python, but I'm not like I'm not an acolyte. I'm not a zealot. I would really like an interpreted language that has types. That is Java or Kotlin or something, and it's Dart too. But like, I want an interpreted language because I like interpreted languages because I can put breakpoints. Again, I'm like lazy to read things. I would rather put a breakpoint. I would love it if these bindings existed for one of those languages. The barrier, I guess, I don't know, in addition to the fact that like you have to be committed to developing and to maintaining the bindings in Java, and if the data science community doesn't care about Java, then why would we as the compiler people that serve the data science community maintain bindings for Java? I don't know. That's also a reason why you wouldn't do it. Was FFI. So the other reason is that there's a technical barrier that apparently Java native interface, JNI, sucks or sucked or sucks or continues to suck or will suck for all time. I have no idea. But like when I Googled around for, hey, this is interpreted language, C bindings, C bindings. Everybody cares about, everybody supports C bindings. What language doesn't support C binding? Java, apparently, until very recently, actually. So, okay, see you later, man. So they just have in their second preview version, like a reconfigured FFI story, and it works. It kind of works. I used it to generate bindings. So I have a subrepo that like has a little test case of like, it'll emit an empty module with an arith constant through bindings and stuff like this. And it uses the C, so it doesn't, so it goes through the C bindings, right? So they have an extract, quote unquote, extract tool that'll parse the C headers and build bindings to the C headers for you. And so I just unleash that on the MLIR C headers, and I get not the bindings with the memory management and Python bindings and stuff that Stella made or whomever made or whatever, but just C bindings, right? And I can, there's a little demo like, oh, you can call up a module. I don't know. I'm not a, willing to learn and stuff like this, but not if nobody's interested. But anyway, so that's the last bullet point. Knowledge transfer from this bindings project to potentially other bindings projects. And that's it. That's the end.
All right. Thank you, Max. Let's move on to question. There are a few questions on the chat. I'm not sure if you want to, let me ask the first one was from Arash. Does Nelly support lowering Python to other custom dialects that are not in tree? Or is there some way to plug that in?
Yes. I think effectively the answer is yes, because what I am doing is breaking all of the CMake conventions and running table gen to generate bindings that are in tree bindings, but don't have Python bindings. So like OpenMP. So you can run table gen, right? And you get the CPP inc, the h.inc, and also the Python bindings. So that's not being done for OpenMP. Again, I don't know why, who makes the call about what's included, what's not, what's generated, what's not, but I am doing that for table gen definitions for in-tree dialects that aren't being generated. So you can do it for your out-of-tree dialects. You have a table gen. Again, this is the beauty of MLIR. I didn't do anything here. I just wrote a little script and I subverted the CMake conventions. So you don't need Nelly for this. I can show you, you can poke around in my repo and I can point you directly at how to do it on your own. Nice picture.
I can elaborate a little bit on the, like, sometimes in the talk and right now you were wondering why are things a certain way. Sure. And most of the things in MLIR have been developed on a demand basis. So it's like we develop for like in an open way, meaning we try to have the project modular and extensible, but most of the time what we try to achieve are conservative in the sense we try to fulfill a need. And so there's always a balance between like fulfilling the immediate need while designing the system to be able to support the future need as well, fairly easy.
It makes perfect sense. I mean, like I have enough hours in the coal mines to like that resonates with me. Like, a full-time programming job doesn't leave much time for like, oh, I'm going to implement this feature that doesn't bake me a cake. Yeah, so I get.
Let me ask for the next question. Is Nelly completely 100% supporting the MLIR Python bindings which are available in MLIR?
No, it's similar to what you just said, where like I'm wrapping up things that are important, that are interesting and important for me at the time. This is a fair amount at this point, where like I have GPU, I have SCF, I have affine stuff, and not a lot, but I've touched a little bit. I'm going to move on to vector, I'm going to move on to tensor, memreps, but no, like ARM Neon or something like that dialect, for example, I don't have anything about. I don't have anything for.
I have a question of my own. you were not very happy with modifying the AST, but I'm not sure why. And in particular, what you're trying to achieve reminds me of TensorFlow, and in particular the autograph thing, where we take a TensorFlow TF function, we annotate the function, and what happens is actually exactly this: a graph, an AST rewrite, and then a tracing of the function to emit an IR. It's a TensorFlow graph under the hood.
It's not that I'm unhappy. I'm fine with it. It's just I think other people, like, I've gotten the strong impression that other people don't like these kinds of meta programming hacks. Like, I understand, you know, it's not a great feat to understand AST traversal, but I understand AST traversal well enough. And so if I were to stumble upon code that does this, this is very kind of like, oh, they're doing that, they're doing this. But other people are very confused and uncomfortable with it. And besides, like, explicitly people telling me this, you have essentially all the people that have rejected Lisp. That's all I'm going to say, right? Like, if as a industry AST rewrites,
right? But I would make a difference in that in Lisp, basically, AST rewrite is part of the user code, right? It's like the user writing Lisp or actually rewriting the AST kind of as they do their code. Here, the way I see it, we want to write a DSL or an embedded DSL inside Python. And as soon as you try to do an embedded DSL, you have to write, for me, a parser or a tool, right? And at this point, the tool responsible to implement the DSL, for me, is totally inbound to manipulate the AST, because that's what it does. It implements a DSL, it implements a language, and manipulating the AST is probably a good way to do that. The user of the DSL should not be aware or have exposure to the AST manipulation, right? As long as the DSL is intuitive and it fits, you know, it should be almost, you know, and no.
So the contrarian, and I agree with you, basically like 96 sigma, 99%, right? Like, it should be enough. But the contrarian answer here is PyTorch, where the initial versions of PyTorch did away with this. And now there's tons of AST traversal inside PyTorch, right? Like the JIT trace and symbolic trace and TorchFX and all this kind of stuff. You poke around. I mean, so before they lumped that on, and they lumped that on because they needed to, because you need graph export, because that's what you need to make pipelines run fast. You need to ditch the Python interpreter. The initial versions and the appeal to like data science users was exactly eager mode evaluation, and the DSL doesn't do a rewrite. Yeah. But no, I'm just being contrarian. There's devil's advocate contrarian and like kind of like absorbing cultural themes.
No, I agree. But with what you want to achieve here, I don't see how we can have an eager mode, right? There's no eager mode to emitting a defined loop feature.
No, you can't. So it's kind of like, so it's a crossing of the desires for sure. Like, I have this fear in the back of my head, but I also have these goals, and there's a contradiction, and I try to reconcile them. So you're right. Like, I mean, I didn't do it. I failed to do it. I have AST rewrites. So you're 100% right. So Alex has his hand up. When you're in class and you have your hand up for a long time, you feel bad for the student that has a hand up. So I know there's some questions in chat, but Alex had his hand up for a while.
I actually don't think there are more questions in that.
Okay, perfect.
Yeah, I had the same question as Arash, and maybe another question was there something missing in the Python bindings that you would need or want to add? Because like Mary said, all of these are completely demand-driven.
Or all what? Say that again. Say the last phrase.
Like, everything in MLIR is demand-driven. So like, if there's something missing in the bindings, we should just add that.
Did you say event? Event?
Demand.
If there is something missing.
Demand. Oh, yes. Yeah. So I have a good answer. It's funny. Again, I had more stuff that I wanted to present, but then I got caught up working on something yesterday. But I meant to work on a patch, like an upstream patch, to support mutation. So I want to do a replaces with of. I want access to replaces with of through the bindings. And Jacques, if I'm saying his name correctly, said that that's a little bit dicey, because there's some, if you order your mutations in such a way that it's Python mutation, CPP rewrite mutation, and then try to do something in Python again, then you're going to run afoul of some map that doesn't get updated with the information. I don't know what map that was. I was going to investigate this, but he also said that pure addition, right? Like, so I said to him something. So yeah, replaces with right. And I would be happy for me personally, just one replace, right? And not like sequences of them. So I would like that. So that's an answer to your question. That's one thing that is missing, but I would like to contribute to that. Like, that's well within the realm of my competency to add that. And possibly I'll be able to, if, you nodded your head, you know which map you're talking about. If you point me at the map, I can try to patch that one too. And if you're going to say that there's a missing feature of listeners, which I kind of like intuitively intuited that was the thing that you need to be able to support, that you need to have.
Not really.
Notify. Okay, well, anyway, so if you point me at the map,
yeah, I'll point you to that. So the problem with listeners is if you run a pass. So basically, there is a map that maps Python objects. So the garbage collection stuff. It maps Python objects to MLIR operations to equivalence. I forgot how many. We have several. And if Python initiates the update, you can patch the map in the bindings. So it's still correct. But if you run a pass, you might still have a pointer to something that the pass erased. So basically, Python bindings are limited to constructing IR, running passes, and printing it.
Yeah.
Anything that you like running passes and trying to get anything else than a handle to the top level module you were running the pass pipeline on is likely going to fail. So we might have assertions in place for that, so it will just assert. But we will not be able to, like, if you had a module and a function, and then you run a module pass, the function pointer is probably dead. Yeah.
And indeed, and so it's funny, you're saying this thing like Python bindings are for generating IR. And I have said multiple times over the course of this thing that that's all I'm interested in, right? And it's true. Actually, this desire of mine comes out of Torch MLIR work, where I was hacking on something and I was like, God, I want to be able to just replace this operation without extending the Torch MLIR pass infrastructure, right? So the one thing about MLIR that is very tough for me and has been tough, and I've made issues and talked and moaned about, is you can't extend compiled releases of anything. You can't add passes that reference a dialect in, and maybe I'm wrong. So you can do transform extensions and there's extension support, and maybe that is generic enough now to support extending other dialects. I might have missed that kind of like news. So I'm aware of transform extension. But as far as, like, for example, I want to extend Torch MLIR dialect, I want to download either their opt file, their opt executable, or their Python bindings, and I want to add more operations. I think that's hard because of type IDs and like CPP fundamentals, and there are other people that have been thinking about it. So Matthew with Tobias and et cetera have some work towards this. So I was doing it Torch MLIR stuff, and I needed a pass that replaced. Like you said, you can use the bindings to create new operations, but you can't. So I can make new Torch ops, but I can't replace the existing ones in the module because replaces. So for Torch MLIR, that work was about actually implementing rewrites, like using Python handles and Python to do rewrites. Nelly's not about rewrites, and I don't want to make it, although it could be, but like anyway. So
it could be about specific rewrites that are more of expansions or lowerings. Than advanced passes. Two quick comments, and I think we're running out of time. Yeah. One thing that you may want to look into is there is a thing called lineage opt DSL, where it generates like the equivalence between a conf and the lineage generic. And that DSL is also kind of Python.
Yeah, I'm familiar with lineage, with the YAML files and all this stuff, and like there are plenty of.
Yeah, YAML is only there so we don't depend on Python at compiler's compile time.
Yeah.
But I personally would prefer your syntax to the OptDSL syntax because I like loops.
Yeah, exactly. So tensor, einsum, and tensor comprehensions and all this stuff. And again, I recognize that, like, you guys wrote that paper. I mean, like, you guys designed that DSL and the semantics of tensor comprehensions and stuff like this. And like, you guys chose tensor comprehensions for a reason. It wasn't an accident that you took summation notation and generalized it and whatever, right? It was thought out for whatever reasons it was thought out.
I can tell you the exact reason. People who were talking with who are doing ML research at that point tended to write math that way. So they would go to a whiteboard and write their math that way. And
Tensor contractions?
Yeah.
That's insane to me, because like I did an undergrad in physics. I did the whole tensor calculus thing, and I'm like, it's fine for proving things, but I would not want to, like, einsum never made sense to me as a programmer's tool. But okay, but again, like, I'm a noob. What the fuck do I know?
Some of those people are also not programmers. And then there is a compression issue when you need to write like entire ResDat. With einsum, it will fit on one whiteboard. With for loops, it will not.
Sure. Yeah. Anyway, so you say, so my syntax is better. I mean, my syntax is just for loops. And so I'm familiar with the Linux DSL, and I steal stuff from there, right? So for example, there's a file where I wrap arithmetic operations. All of those top level, like, hey, infer what the result types are, if it's a float and an int, or if it's a constant, it's an index and an int, right? There's all this code that feeds into the bodybuilder. You have a bodybuilder. I lifted that. I copy pasted it from you guys. So I've poked around. I've poked around in absolutely all the code on the Python binding side, actually.
Yeah, and then my last comment, and maybe all the time, I think there is a place for this upstream, if it's clean enough, somewhere next to LSP server. So it can be used as a compiler developer tool. So I would write this instead of writing raw IR for a test, run Python locally to generate the IR, and I would commit the IR. So it's not running in the test. We don't have a Python build dependency, but it makes my life as a compiler developer easier. And we had multiple attempts over the years to do a sort of embedded DSL in C++ or in Python upstream, and it never worked. So it really should be an adjacent thing that we don't want to depend on, but we can use.
I see. Depending on, I fully agree. And this is something we wanted. Like, I really wanted to work on this. I never found the time to get there. Depending on how extensible it is, meaning, like, is it something where I can come with my out of tree dialect and hook into the system, add some overloads or some new operators or things like that to the system, and get my IR, mixed with upstream types. I don't know, maybe I need an operation to work on memref and I need to hook there. Depending on how it is, to me, I could see it on the same level as the Python bindings, in that it can be a tool for downstream people to build actual, tracing and running mechanism. It's a tool in the toolbox. But I don't know how extensible it's going to be.
So it is, and it's not by virtue of anything I've done. Whoever hooked up dialect registration through the Python bindings, there's already an API for this. Essentially, I don't know, you're nodding your head, maybe you know about this thing, but if you build a library called site underscore site underscore initialize underscore 0 underscore site underscore initialize 1, those will be called whatever. They'll be loaded, and then there's a method that you register, right? There's a PyBinded register dialect method that is called immediately, and all of the CPP code is registered. And so that is the mechanism that I use, by the way, to register OMP dialects that aren't by default registered in the default Python bindings. So again, another example of, like, hey, it's in stream, but it's not registered in the default Python bindings, but I hook it up and do indeed register it with the dialect registry by using this site underscore initialize infrastructure.
Okay, interesting. I think we're much over time right now, 12 minutes. It was very interesting. I'm looking forward to see, what pieces can end up in the repo, or all of it. I don't know. We have to take it step by step, but to follow up on that and look more into it. Thank you for the great talk, for the work you've been doing on this. I love to hear also about the failed attempt and the path that you took along the way. That was very entertaining. So thanks again, Mac.
Thank you.
Thanks
Okay.
everyone for attending, and see you next week.
See you guys.